Hey everyone, in this video I'm going to talk about prior information and Bayesian synthesis. And this is kind of the last step of our comparison of classical maximum likelihood methods and Bayesian posterior simulation. Because in the previous videos I talked about how kind of maximizing the likelihood surface is different from taking simulation draws from the posterior distribution. But what we didn't really talk about in so much detail is how this posterior distribution is different from the likelihood, okay? And the key difference between the posterior distribution and the likelihood surface is that the posterior distribution takes into account prior information, okay? So while classical statistical methods like maximum likelihood produce summaries and inferences based on basically a single data set, Bayesian methods combine a model of the data with prior information, with ultimately the goal being to obtain inferences that are consistent with both sources of information, right? So in that sense, whenever we talk about the posterior distribution, what we mean by the posterior distribution, or what you can think of as the posterior distribution, it is kind of a compromise between the likelihood or the data that we observe and the combined with the underlying probability model generates the likelihood surface, and the prior. And the prior exists before the data collection, and it represents kind of the set of likely values that the parameter estimates can take prior to observing the data, okay? And the best way to kind of think about this is to kind of examine different types of distributions, right? So we talked about maximum likelihood estimation and talked about kind of specifying the likelihood function for a given observed data set and an assumed probability model, an assumed data generating process, and then just like in the kind of trivial Supreme Court example, we generated a likelihood function for one specific parameter and then said, okay, the most likely parameter value that generated that likelihood function is something here between 0.4 and 0.5, right? The point here is that we don't only have, in Bayesian posterior sampling and Bayesian inference, we don't only have this likelihood that is based on the observed data that we have, right? We don't only let the data itself kind of speak and determine our inferences, but we have a prior distribution. And you can think of this, as I mentioned, as the distribution of possible or likely values that you would expect for that specific parameter of interest, okay? So if we put kind of both the prior distribution and the likelihood distribution on the same scale, we can then combine them into a posterior distribution, and Bayesian, and that's ultimately what the Bayesian estimate does. It combines the prior, the prior estimate and the data estimate, which is kind of characterized by the likelihood, into a posterior estimate. Okay. And what this posterior distribution ultimately looks like is basically a compromise between the likelihood, the data that we, the data estimate, so to speak, and our prior estimate, right? So while our maximum likelihood estimate here would be theta being 0.475 or something like that, we have a prior with a mode of around 0.5, something larger than 0.5, and then we have our posterior, which is where the posterior mode is somewhere between the likelihood and the prior. Okay, so it is a compromise between the prior and the likelihood. Okay. And we also have to keep in mind that basically the location and the precision of the posterior depends on the precision of the likelihood and the prior, as well as the uncertainty around the likelihood and the prior. Okay, so one way to kind of think about this is to think about the precision of the posterior, and the precision of the posterior in general is equal to the precision from the prior plus the precision from the data. Okay, and in this particular example, we see that the likelihood is more informative in the sense that it's more precise than our prior distribution. So that means that the posterior distribution will be closer to the likelihood than to the prior. Okay, so we kind of can think about uncertainty as the spread in the likelihood and the spread in the prior, and depending on how much precision there is in the prior and in the likelihood, we get the posterior distribution is ultimately affected more by whichever distribution is more precise, right? So another thing that this will tell you then is, of course, if we increase our sample size more and more and more, what happens is that our likelihood distribution gets more and more narrow. So as we increase our sample size, of course, in kind of this hypothetical example, the posterior also becomes closer and closer to the likelihood, okay? To summarize, in Bayesian inference, the likelihood is, and I'm again in the way, in Bayesian inference, the likelihood is multiplied by a prior distribution to yield the posterior distribution. And this posterior distribution we ultimately take as a summary of our inference given the model and data, okay? So we not only take into account the data itself, but we also take into account prior information as to what types of, what range of parameter values is likely or not, okay? And so going in the rest of this video, I'm going to talk through one specific example where the choice of these prior distributions can matter and where it can actually make a difference, and how we can think of kind of deriving these prior distributions. Of course, in many cases, this requires substantive knowledge, maybe about prior research that has been published or previous studies that you ran or something like that. But we can also include prior information, or we can also kind of take care of situations where we just simply don't have a lot of prior information, right? We can use priors that are weakly informative that shouldn't really change our estimates all that much, or in the extreme, we can use completely non-informative or flat priors. If we use completely non-informative or flat priors, you can think of this prior rather than having this bell-shaped curve being just completely flat. What happens then is that the posterior is equal to the likelihood, right? Because if we multiply the likelihood times a constant prior, then the posterior will just be equal to the likelihood, right? So if you're kind of unsure about introducing prior information, one way to think about it is if you increase, or if you just include uninformative, completely flat priors, what you will get is you will get to the result that your posterior converges ultimately to the likelihood and converges to the maximum likelihood result, right? So it's a framework that allows you to take into account prior information, but it's not a framework that forces you technically to do so. You know, you can be vague about your prior information as well, okay? So the example that I'm just going to go through quickly is also discussed in the textbook, so I'm just going to go through a little bit of the coding really briefly, but make sure to read through that example in the textbook in chapter 9 as well. And this is specifically an example of the influence of parents' beauty, subjective attractiveness, and the sex ratio of their children, their offspring, okay? And so this is an example of a study that received quite a lot of publicity because it suggested, based on a survey from, I believe it was 3,000 Americans, and observed a correlation between the attractiveness of parents and the sex of their children. And specifically, it suggested that the more attractive parents are, the higher the likelihood of having girls rather than boys, okay, as children, okay? And we will use kind of a simplified example. There has been some debate about this, there was another paper in response that kind of was critical of this finding, and we'll kind of look at a simplified version of this analysis to illustrate how, in this specific context of a study like this, we can introduce prior information and how prior information can ultimately kind of help us get better predictions, okay? The data is available on our Studio Cloud, oh no, sorry, this data is actually simplified. It's not even the 33,000 people survey, it's just an aggregated version of this data set, just to illustrate the point. We don't even have to load any data because ultimately we're just working with 5 data points. And what we've done here is we basically aggregated for each kind of attractiveness level, which ranges from -2 to 2, so 5 different categories. We computed the average proportion of girls for each of those groups, okay? And we can we can run a basic linear regression with these 5 data points with, of course, the percentage of girls as the dependent variable, or the outcome variable, and the attractiveness score of parents as the predictor, okay? And we can see, okay, including the point estimate on our left side and the fitted line on our right side, we can see, of course, that the point estimate suggests a positive relationship. We have a slope of around 1.5 and a intercept of around 49, of course, because the chance of having a boy versus a girl is close to but slightly less than 50%, and we see kind of the slope here with an increase in this attractiveness score. We see an increase in the percentage of girl babies, okay? Okay, so the point here is, now this is basically an example where Bayesian regression, since this is kind of a simplified example with only a few data points, this is an example where kind of introducing priors will change the model output and will ultimately lead us to make more accurate predictions, because as you can see, of course, there's also large uncertainty around this slope. So even from a frequentist perspective, we wouldn't consider this slope coefficient statistically significant. But still, if we were looking at point predictions, we would have quite large effects or estimated effects of the I shouldn't give it a causal interpretation, but we have a predicted differences conditional on attractiveness in the percentage of girl babies. Okay, so the first thing we can do in this example, so of course this is a basic OLS regression. Of course, this is just based on minimizing the sum of squared residuals. We could kind of think about this as in this case, we kind of think about this. If we think about the basic linear regression as a maximum likelihood estimate, then this would be equivalent to basically a posterior, or in the Bayesian framework, to a completely non-informative or flat prior. So if we kind of estimated this in a Bayesian fashion with completely flat priors, then our point estimates should kind of be equivalent to what we observe here. Of course, we're in a very small data set, but just to kind of illustrate the point. Okay, so so this is kind of the flat prior, non-informative prior, purely likelihood, or in this case, linear regression or OLS result. Okay. Now, but the problem is that the estimated, at least the point estimates, one, there's a lot of uncertainty around the slope and the the intercept. And the point estimates suggest a much stronger relationship than we actually think is realistic. Okay, so how can we estimate this model using Bayesian regression with a weakly informative prior? And the weakly informative prior that we will use are just the default priors. And the way you can think about the default priors that are just kind of coded into the stan GLM function that we're using, you can think of those as kind of soft constraints that keep our inferences in a reasonable range when the data are sparse, okay? So it really keeps the inferences, all it does, it keeps the inferences more stable, but it doesn't really change the estimates so much, okay? So if we run this model in stan, we use, of course, stan GLM. We run this model. We save our simulations by converting the model output to a tibble. And then another additional thing that we can do based on the model output is we can examine a prior summary if we want to look at what type of default priors stan actually used in this context. And we see that both for the intercept and the coefficients, we see a normal prior, we see a specified prior and adjusted prior. The reason why there is an adjusted prior is that it takes the adjustment basically takes into account the scaling of the original data. Okay, so we see quite wide priors. For example, here for the for the intercept, a normal distribution with mean 49, which makes sense, but a scale, so that's the variance of, or standard deviation of 11. Of course, that's quite a wide range, and similar for the coefficient, which with a mean of 0, a scale of 7 is very large. Okay, so this shouldn't really make any difference compared to the kind of OLS estimate, or it's basically equivalent to a flat prior non-informative prior result. Okay. Now, if we kind of plot the posterior draws, similar to the way we've done it in the previous videos, we get, again, 4,000 draws from this posterior distribution for our intercept beta 0 and our slope beta 1. And we see that this range is quite, there's a large variation in positive and negative slopes. We have here 0, and quite a large variation in intercepts as well. Okay, and we can again kind of draw each and every one of those kind of simulated regression lines, and we see they're basically all over the place. So there's a lot of uncertainty around our estimates. Okay. Now, on the one hand, we can say, okay, well, this is, you know, maybe just because it is so there is so much uncertainty. You know, the model doesn't really tell us that there's a clear, strong effect, so that's fine, right? Why do we need to invoke priors? Well, if we think about this as a prediction task, where we now want to predict the probability of a child for parents with a given attractiveness score, obviously using this model with that inferential uncertainty is kind of overstating the uncertainty around our predictions, and will ultimately lead to very low quality predictions, right? Because there's so much uncertainty between you know, the expected percentage of girl babies in this case, that we couldn't really say anything at all, right? But we know, you know, just from census data and so on, that the percentage of girl births is fairly stable, right? So we know that there is more stability in our outcome measure, right? So if we want to create predictions based on our predictor, we can take into account that we know that there is less variation in the outcome measure than kind of what is represented in this uncertainty. Okay, The next step is then to use the same model, but now use informative priors, okay? And the way we can specify these priors is to just specify priors as additional arguments in our stan GLM function, okay? And in this specific example, we have quite a good idea of what exactly these priors should look like, right? Because we know, looking at first at the intercept, we know that the percentage of girl births is fairly stable, around 48.5 to 49% girls across all births, right? We can take that information from census data and so on, right? So we know that this doesn't vary all that much, right? We also know that it doesn't really vary all that much, you know, across other types of characteristics, you know, like race or you know, other types of socio-demographic characteristics don't affect the percentage of girl births in any, you know, substantive way, right? So given that there is very little kind of variation between you know, other kind of characteristics like race or you know, or it could be income, or you know, any other characteristic you could think of, it would be unrealistic to assume that something as subjective as attractiveness would have such a big effect, okay? So that's why we can first, for the intercept, specify the prior distribution for the intercept as 48.8 with a standard deviation of 0.5. Basically specifying that the percentage of girl births shouldn't vary much more than, you know, between 50 and 46 or something along those lines, right? So that's for the intercept, and then we can also say that the effect of realistically comparing it to, you know, differences across other characteristics, the effect of attractiveness for 1 unit increase in attractiveness shouldn't be much more. Well, first, the average prior is 0. It shouldn't have it. We don't expect it to have one effect necessarily, but we allow for variation. But that variation should be fairly limited, right? Around 0.2 standard deviations. The standard deviation of 0.2. Okay. So since our predictor ranges from -2 to 2, that essentially means that we shouldn't observe differences in the percentage of girls in the population between like the minimum and the maximum. We shouldn't expect much more than 0.8 or a 1 percentage point increase or decrease, okay? Comparing the highest and the lowest category of attractiveness, right? So here are these informative priors kind of based on kind of what we know about the variation in the percentage of girls that are born, and the baseline, basically, we can set very quite precise and informative priors in this specific model, okay? Of course, we see then these different prior specifications are also represented in our prior summary. But the point is, what does this actually do with our estimates, okay? And here we have the equivalent kind of image for our draws from the posterior distribution for our intercept and our slope. And of course, they're much more narrow, much smaller, closer. The intercept is closer to 48. The slope is closer to 0. It still ranges. And for our kind of 4,000 sets of regression lines, we see, they're all more or less flat. There's a little bit variation, but we don't expect so much of a difference, right? So the key point here, though, is that this is, if we think about this as a prediction task, okay, this model result is ultimately much more informative than this result, right? Despite the fact that we don't really observe a clear positive effect of attractiveness on the percentage of girls that are born. The precision of the predictions based on this model, including priors, is much greater. We have much more precision because we took into account what we know about the natural variation in the percentage of girls that are born, and how much this varies across characteristics of the parents. And taking into account that prior information allows us to make much more precise predictions about new data sets than a completely naive model with weakly informative, or even more extreme, completely non-informative priors, right? So I hope this helps as an example to kind of illustrate both how we can kind of come up with prior distributions in a specific practical example, and then also to show how this actually can make a difference, particularly when it comes to predictive accuracy. Okay. In the future, of course, we will look at additional examples that are more more from a political science context than the specific toy example, but I think this is still a good illustration of kind of the underlying concept. Okay, so this concludes our videos for this week. I'm looking forward to our Q&A session, where we're going to talk a little bit more about some coding examples, and we'll also talk about solutions for the first problem set that you handed in. All right, that's it for now.